accelerating Ethernet with iWARP technology.
iWARP is a standards-based technology that brings remote direct memory access to Ethernet.
In a nutshell, RDMA allows an application to place a block of data directly in the memory space of another application in a very efficient manner. The destination can be an application in a virtual machine in a different server anywhere in the world. Two key features of iWARP RDMA that make it so efficient are kernel bypass and direct data placement. Let's talk about kernel bypass first. With generic Ethernet LAN traffic, the processor busily aligns incoming packets into queues and assembles them for transmission. The processor gets interrupted when a queue is full and has to stop to service the interrupt. All this traffic management drives up CPU utilization and slows down network performance. iWARP RDMA provides a different approach. Kernel bypass lets iWARP-capable adapters manage the RDMA network connections, avoiding the system software as much as possible. iWARP itself does the connection management between the source and destination by establishing queue pairs between them. Via queue pairs, iWARP bypasses the host processor and transmits packets of data directly to the application's user space. No queues for the processor to manage or network-related interrupts to handle. The result is lower latency, greater bandwidth, and lower CPU utilization. The advantages of kernel bypass increase with the size of the messages, which is a key reason iWARP shines with large storage blocks and virtual machine migration. Furthermore, iWARP's connections between source and destination are secure, protecting users' data in flight. The second key reason for iWARP's networking efficiency is a feature called direct data placement. With traditional sockets Ethernet, the host processor doesn't know where the application resides that wants to consume an incoming packet, so it creates a queue in kernel space. That requires the processor to copy all the data from the kernel queue into the application's user space. Because iWARP already knows where the data is going with its queued pairs, it can directly place the data in the application's user space without making unnecessary copies. So what does it take to unleash the power of iWARP RDMA? Of course, it takes Ethernet controllers that are iWARP capable. For iWARP, that's the only new hardware required. iWARP works with all existing switches and the entire Ethernet networking infrastructure as it is today. The biggest challenge for taking advantage of iWARP is that it requires applications to be written to use RDMA verbs, rather than the standard Ethernet LAN interfaces known as sockets. That's where system software comes to the rescue, starting with Microsoft delivering SMB Direct technology in Windows Server 2012. Microsoft has done the verbs programming so you don't have to. SMB Direct will automatically survey the network for RDMA-capable devices. It will automatically use any iWARP-enabled path from source to destination it can find, and deliver all the performance and reduced CPU benefits of iWARP for storage and virtual machine migration. RDMA technology is so powerful it has attracted the development of two competing technologies for RDMA Ethernet. In addition to iWARP, there is RDMA over Converged Ethernet, or RoCE, that starts from a very different premise. iWARP is built on top of TCP/IP and takes advantage of all the power of TCP/IP Ethernet infrastructure, including routability and congestion management. iWARP is a scalable cloud RDMA that goes anywhere the internet goes. Although RoCE uses the physical layer and the media access layer from Ethernet, it differs by building an InfiniBand network and transport layer on top of them. So RoCE has to reinvent all the richness of TCP/IP from scratch. Intel sees several fundamental advantages in iWARP over RoCE because iWARP leverages mature and scalable TCP/IP technology. RoCE's first challenge is that within the local subnet, sometimes called the L2 subnet, RoCE requires fully deployed data center bridging technology to make its network lossless. In practice, that means that data center admins need to physically configure every switch to support the DCP traffic classes. This is in direct opposition to industry trends towards data center automation and away from highly labor-intensive manual configurations. Another key advantage of iWARP is that, riding on TCP/IP, it is routable, meaning it can leave the L2 subnet and fly across the internet through L3 routers. The original RoCE is grounded. Recognizing this deficiency, the RoCE community has recently released a specification for RoCE v2 that does add routability. However, they didn't use the TCP transport. Rather, they picked UDP, which provides no reliable delivery or congestion management during routing. iWARP uses TCP's end-to-end congestion management, which makes it scalable. Rocky has no congestion management deployed in the L2 subnet, and Rocky v2 has not even specified a congestion protocol at L3. The only method to address scale is to overbuild the network infrastructure, therefore underutilizing the network investment. If either Rocky encounters network congestion, their only option is starting over and retransmitting an entire set of packets, hoping for better luck on the retry. iWARP is available today from Chelsio and soon from QLogic. Intel is integrating iWARP technology into future server chipsets and SoCs, driving broad availability of this technology. Microsoft's SMB Direct is just the first major software effort to let users take advantage of iWARP technology. The future is bright for iWARP.